So for people, yeah, I'll just go ahead and get started. So for people watching the recording or watching live, today we're going to be doing a stream on how to profile, benchmark, and optimize Haskell programs. Um, and I will be driving, meaning be doing the programming, but also I'll have one of my coworkers, Thomas, will be here. He'll be here to just ask questions and help generate discussion. I'll also be taking questions from the audience as well and answering people's questions as I go. So first off, let me just change to a temporary directory, and I'm going to have two windows open for this. Basically, most of them are just going to have criterion installed. That's the only Haskell package we'll be using for this particular example. And so throughout this example, we're just going to use a simple re-implementation of the list data type as a motivating example, and then we'll just sort of build off of that. So we're going to not use the one from the prelude. And the reason we're not using the one from the prelude is that the prelude has, or for base, is that the list type from the base has several rewrite rules which can affect optimization. And so I wanted to start from a clean slate where there are no existing rewrite rules, so we can see how GHC works by default, and then we can add to that. So yeah, here's what a list type would look. Oh yeah.
Just as a quick note, any way that we could move the like the GHC ID window over a little bit to the left? Currently, the video screens of you are a little bit covering.
Okay, so I'll put this. Is that here?
Yeah.
Yeah. There we go. Okay.
Yeah. Perfect.
And okay, so we'll do GHC ID example.hs. Okay, there we go. Yeah. So first off, we'll call them Haskell module main. It's just to satisfy GHC ID. Oops, sorry. Okay, good. All right, so one of the simplest ways you can measure performance is benchmarking using the criterion package. So for example, in this case, I happen to already know the relevant module names and function names where I wanted to import because I practiced this in a dry run beforehand. The two useful modules for criterion are going to be criterion and criterion.main. The only thing we use criterion.main for is for the default main function, and everything else comes from the criterion function. Default main takes a list of benchmarks, and each benchmark is of the form criterion.bench, and then let's say the name of the benchmark, I'll just say list, and then the actual thing that we're going to benchmark. And the way that criterion works is you give it a function that you want to benchmark, and then a function argument that you want to apply it to. And criterion will just call that function on its argument over and over and over again, evaluating the result and seeing how long that takes.
And is that required to be single argument only, or you can do any number of arguments?
I think it's single argument only, meaning you'd have to curry the function. Oh, let's check really quickly. So the function in question is called WHNF. And I want to see if there's a curried version of that function. So here's the one. It basically says, given a function from A to B, so that's what you want to benchmark, and then an argument of type A, then you have something that is benchmarkable. This is called WHNF because that's an abbreviation for weekend normal form. Actually, sorry, I should probably, before I continue, I should probably ask the stream, can people hear me? Is anybody watching the stream that can hear both Thomas and I talking?
Yeah, you should be able to hear both.
Okay, thank you. Okay, so going back.
Looks good.
Yeah. Okay, so where was I? Oh yeah, so WHNF is an abbreviation for weekend normal form, which means you evaluate it up to the outermost thing, but you don't dig any deeper. So for example, the outermost thing could be a number, or more generally, a constructor. Or it could be a lambda, and maybe some other things which I'm forgetting. NF is short for...
In the case of our list, what would weekend normal form be for that?
Oh yeah, so for our list, let's assume the list was something like example equals cons1, cons2, nil. If we were to evaluate that to weak-head normal form, it would just be the cons constructor. And like in the inner fields would just be thucks, possibly unevaluated. Maybe they're already evaluated, but they're not necessarily evaluated. And so if you want to like fully evaluate things, then there's a normal NF function, which is short for normal form. In order to use that function, you need to implement the NF data type class. It's a type class that you can derive automatically. So for example, let's actually show really quickly how you would derive that class. You can actually do it like, we're actually going to use a cool language feature called derive. Actually, let's first go to the documentation, which I believe tells you how to derive it. Or I thought it. Wait, why is it in this type class? That's actually kind of a little bit weird. Let's go to the deepseek package, which is where it originally comes from. Okay, so if you go to control.deepseek and you look for NF data, it gives you nice documentation showing how you can auto-generate the right instance for your class. So basically, you can just say derive generic, and then you can also derive NF data too. So first off, we'll just turn on the two language extensions. I'll explain in a second what these two do. Oh, so in order to do this, then I need to actually change my environment to include the deepseek package. So let's actually just quickly do that. Same thing here. Actually, it should probably already be there by virtue of being a dependency of criterion. But okay, so import control. Was it control? Yeah, control dot deepseek NF data. And then we'll just say, so if we do this correctly, then all we have to do is say deriving generic and NF data. Let's also just get GHC ID going. Criterion. Oh, sorry, it's talking about this income because it's just there's mismatch parentheses. Oh yeah, so I need to import generic because it's not. Oh, sorry. Yeah. There. Okay, we're good. So, so in order to derive the generic class, you need this derive generic language extension. And then what derive any class does is that whenever you derive something like NF data, that's a shorthand syntax for just saying NF instance NF data list. Technically it would be like NF data A. NF data list A with an empty function body, right? And so that's just a nice shorthand for that, so you don't have to write all that out. You can also be explicit and tell GHC which deriving mechanism you want to derive. So there's something called deriving strategies. I'm actually getting a little bit off board from optimization, but I just want to quickly cover it. So it'd be like deriving stock generic, and then deriving any class NF data to basically tell GHC which method you're using. So because the reason why is sometimes there can be multiple deriving strategies that are valid for a given deriving, so that disambiguates them if that's the case. So that's what we would do if we wanted to use the NF data instance. We're actually not going to use it, but that's just for future reference.
So it may be interesting to benchmark weak-head normal form versus normal.
Yeah. Yeah. Let's try that. So now we need to implement a function to benchmark. So let's call this. Let's make a length function. I'm just going to call it list length because I'm lazy. So given a list of A, return here. So first off, we're going to implement this in the naive way. So list length nil equals 0. List length cons x. Sorry, I actually should keep chat open just in case people have questions. So I'll just keep this over here. Sorry. List length, we're going to ignore any elements, equals 1 plus list length x's, like that. Okay. And now, so if I want to benchmark that function, then I would just say criterion weak-head normal form list length, and then give it a list. So let's create a list of 1,000 numbers. So let's say, call it list numbers. It's a list of ints. List numbers equals go 0, where go n. If n is less than or equal to 1,000, then we return cons and go n plus 1. Otherwise equals nil. Okay, so I'll generate 1,000 numbers. So like if it was a normal list, we would just write, 0 dot 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 1,000. And actually, I think you could. Actually, can you? No. Well, if you use like a combination of the overloaded list language extension and then implemented enum, I think if you did overload list, you could overload that notation, but I might be wrong. I'd have to double check. Anyway, but I think you might be able to.
I was about to ask. That would be cool.
Yeah.
To be able to use that for range.
I'm not entirely sure that's correct, but it would be cool if you could. So let's go to now let's benchmark this function, and let's also like test weekend normal form versus normal form just to see what's the difference, if any. In theory, because the result is an integer, the integer should already be in both weekend normal form and normal form. At least once it's if an integer is in weekend normal form, then it's also in normal form. So there shouldn't be a difference between benchmarking these two functions.
But if the list had something expensive, then we might expect the benchmarks to be quite different.
No, even if the list had stuff inside it, I wouldn't expect these two benchmarks to differ because they're not making the function argument to weekend normal form. They're making the function result go to either weekend normal form or normal form. And the result is just the integer.
It's the result. Got it.
Okay, so let's now run our benchmark. So when we compile the benchmark, we want to do with -02 to make sure we're turning on all optimizations.
And that would be to make sure that you're just benchmarking exactly what you'll be sending out, in a production use case.
Yeah, you don't want to be benchmarking unoptimized code because that doesn't tell you much. So one thing that's cool about criterion is that, it provides like this nice little statistical output, which is neat. Usually I just only look at this number when I'm doing benchmarks. So here, it's basically indistinguishable. That's within the noise. So it says the standard deviation is almost as big as, well, I don't know why these have much larger standard deviations, but it's basically within, the difference between these two is essentially within the noise. This is actually weird
how would I interpret, so some of this output? So there's a number of fields, and then at the bottom there's the variance introduced by outliers. Do you mind just quickly overviewing how you might interpret that?
Yeah, so these numbers are a little bit easier to interpret. So mean is it is the arithmetic mean. Standard deviations are these are standard. This number is not the mean. So what criterion does, it's actually easier to show. If we open up, there's an HTML output that criterion can produce that I think it makes it more clear how it computes that topmost number. So whenever you run your program with default main, it adds several command line outputs you can use to customize criterion's behavior. And one of those is this -- output flag right here, right? So if you say output example.html. So yeah, just give it a second to rerun. So what that will do is it will open up, it'll give you a web page, and so that'll be over here. That looks something like this. So what criterion does is it will actually run the function not only multiple times, but so it'll have sort of the different runs. So first it'll run the function once and measure how long that takes. Then it'll measure the then it'll run the function twice after that, and then measure how long that takes. And so basically you'll get a plot of if I run the function n times, it takes this long, and it'll do it'll choose for various values of n. It'll try that, and it'll kind of bias towards low values of n, sometimes pick high values of n. And so then from all of those different runs, it'll build this regression of number of runs versus time, and it'll fit a line to that. It'll fit a line to that regression. I'm probably using wrong terminology here. And then from the slope of that line, that's how it computes that number that you see here at the top. So that number is the slope of this line right here. I'm not sure why criterion does things that way, but I'm pretty sure there's a good reason for that. Keep in mind, you're probably thinking to yourself, what if this is a lot of runs, because each of these dots represents at least one run, probably more. These are actually thousands of iterations of this function, or tens of thousands of iterations of this function for some of these dots. So for cheap functions, the graph will look more like this. Let's say it's an expensive function that takes at least a second to run. Criterion will then just run it up at most 10 times. It'll run, like first run it once, then run it twice, then run it 3 times, then run it 4 times, and then that's the maximum. Sorry, that's the minimum number of times it'll run it if the function's really expensive. And it'll just create a slow. It'll basically plot 4 points and then fit a regression to just 4 points. If your function's really cheap, then criterion will run it like tens of thousands of times and build a much finer regression from that. So it basically has sort of a time budget to work within to run your function, and it'll just run it as many times as it can within that time budget to build the most accurate regression possible. And then from that, you can get like this nice distribution of run times, which can, so if it tells you like you have a large number of outliers, that means you just have like kind of, your distribution is a little bit too broad. This one actually, the one looks okay. I don't know what it means. I guess it's because it has a fat tail in this direction, maybe. This one also kind of has like a weird tail over here. Maybe that's what it's talking about. I'm not really sure exactly how to interpret this number sometimes, other than like it's not good for it to be high. One reason it may be high is because like I'm running Zoom and I'm also streaming at the same time, so that may be like causing lots of outliers in the benchmark. I might get a sharper curve if I did it with like a clean background system.
And we had a question. Will it fit polynomial lines or only straight lines?
I think it's only straight lines. Probably the way I would check that is to just look at see if there's any command line options to change how it fits things. So yeah, here's, you can, like, let's say you have an expensive function, you want to give criterion more time, you use this time limit option. I don't know what this means. I don't have a strong background in statistics. Yeah, it looks like none of these let you change the fitting algorithm, so I'm guessing it's always just a line. Yeah. Okay, so I'll let you let me know about any questions so that I don't have to keep switching with the browser. But
yeah.
Okay, so going back to this. Where was I? Okay, so yeah, we basically verified that there's no measurable difference between weak normal form and normal form. So now one common optimization for a function like list numbers is to use what's called accumulator. I don't know what the name of this style is called, but I guess I'll call it accumulator passing style. It looks a little bit like this. I'm sorry, not list number. This is we're going to change how we compute length. So list length to. I'm not very original about how I name things. So equals. So basically, sorry, I'll be a little bit more explicit here. So we pass in an argument as the starting state. So like, and we say, okay, now if we hit a nil, then we return that's basically our tally or our accumulator. We say go n cons x's equals go n plus 1 x's, like that. All right, so one thing we're not doing at the moment is we're not being strict in this accumulator just yet, and we're actually going to benchmark. Well, first we're going to benchmark this versus the previous version, and then we're also going to benchmark a third version, which is with a strict accumulator, like this. And so for that, we will use the Bang patterns language extension.
And Bang patterns in general is, with the exclamation point, forces a thunk to be evaluated?
It forces it to weak head normal form. So it basically says
weak head normal form.
Yeah, so it's as if I had written so this, using this, I'll do it up here. So it would be as if I had written go equals n seek before each of these lines, like that. So it says before you recurse, make sure you evaluate n to weak head normal form. Or not before you recurse, but like before you evaluate the right-hand side of the equals side, make sure you evaluate this function argument. So now let's compare all three of those. So this length, 2, 3. Okay. Oh, sorry, I didn't. Let me fix the names. So 1, 2, 3. Okay.
And one here is the original.
Yeah, so one here is the original non-accumulator passing style. So they all look kind of roughly the same. They're within the error. There might be some difference here between 2 and 3. So let's say we're not sure if there's a difference. So there are other ways we can kind of tell whether or not something should be efficient or not. So like one thing I like to do when I'm optimizing functions is to look at what's called the core and see like how so the GHC has a lower level language that is an intermediate language along the way. So it starts with like the Haskell syntax, which is what I'm editing right now. Then the next stage in the pipeline. Actually, let me just go ahead and add a little comment with the stages. So it'd be like, Haskell. Right. Next stage is technically called System FC, I believe, or GHC Core is another name people call it. I believe after that is it's either C minus minus or STG in some order. I believe it's STG is next, and then C minus minus maybe. They're in some order, and then finally either a native code generation, so like assembly, typically assembly. If I'm wrong, like please correct me. The part because I almost never go past core when I'm looking at how to optimize things. You should actually look for people who are really good at Haskell performance. They will look more layers deep, and you can ask GHC to omit these further downstream layers. For me, System FC is usually good enough for the kind of things that I do. So if I want to get core, the way I would do that. So first of all, what I'm going to do is core will basically show me optimized versions of everything in this module. What I'm going to do actually is comment out this code just so it doesn't show up in the generated core because it's already going to be a little bit large. Oh, sorry, I do need a make function. Or I would need to rename my module to not be called main because the Haskell compiler expects a module with a name main to have a main function in it. And then if I want to get the core and the optimized core, so with -O2, you say ddump simple. Usually I'll add 2 more flags along with this flag. So the first one will be suppress all because the default output for the core is very verbose, and so this kind of gets rid of a lot of stuff that people typically tend to omit. And the second is I usually just add this because very often I might ask for the core repeatedly for the same program, even though I haven't made any changes since the last time. So this basically says just always rebuild it even if nothing changed since the last time. So at force recompilation. Oh, sorry, and you also need the file. All right, so let me make this a little bit bigger.
Yeah? Is simple too long of a word for that flag?
Oh yeah, they really like to abbreviate things. So yeah, the E was just too much for them, I guess. Yeah. So yeah, you can see this is kind of what core looks like. This is essentially, you can think of it as like, it uses syntax very similar to Haskell. It's kind of like a simplified subset of Haskell like a lot of it is it's basically kind of like a subset of Haskell. Where a lot of higher level features have been desugared to lower level, more orthogonal features, right? So like instead of a pattern match, it'll always be a case statement, right? There are lots of things in Haskell that are essentially your syntactic sugar for a case statement. Or there's one main difference, at least when you're reading core code compared to Haskell code, is that in core there's no like no type inference, meaning that like type abstraction, so like and type application are all made explicit. So like for example, if you have a function that's polymorphic over some type, then in core it'll literally be represented as like a function that takes the polymorphic type as an additional argument. So you don't see that additional argument in the Haskell code, but it will show up in core code. I'll show that as we go while we're looking through this core code.
Yeah, that would be cool to see.
Also, the other thing about core is that they sort of really mangle variable names, so that sometimes makes it a little bit hard to read. But usually they'll try to keep the original variable name somewhere in there. So like you'll see instead of list length, it'll be like $W list length, for example.
Is it possible to get the source up next to this?
Yeah. Let me make this. Let me make it like this. Okay, and let me just. Okay, sorry if I'll cover your face for a second so we can watch side by side. Okay, so yeah, so here we go. You have list linked here, list linked here, and oh yeah. So actually, sorry, this is oh, this is kind of interesting. So this actually corresponds to this right here. Well, anyway, the key thing I want to point out here is that, so here's our list length 3 function, and this corresponds to this guy over here, right? But what it does is then it actually detects, so it says, so it figured out, so GHC is actually sufficiently smart that it does something that's called strictness analysis. So it will actually take this function and realize that it would be much faster if the accumulator were strict. So it'll just go ahead and make the accumulator strict for us, which is nice. So a lot of times you actually don't need explicit strictness annotations. This was not the case like several GHC versions back, but I think like at least by GHC 8 and later, GHC strictness analyzer got really good. And there have been a lot of times where I thought adding a strictness annotation would help things, and it actually didn't. And usually the way I confirm that to myself is by looking at the core. So here we have GHC is optimizing both list length 2 and list length 3. And here GHC is smart enough, and it says like it just first optimizes list length 3, which is already the strict version. And then it says, okay, list length 2 is going to be the same code. In fact, it's just a synonym for list length 3. So they just basically share the exact same code. So this is like very strong proof that those two functions have the exact same performance. Whereas if we looked like at list length 1, which I imagine is going to be, I don't know, somewhere way up. Or maybe that's what this one of these is. I'm not sure which one I'm looking. Oh, here's the original list length function. Yeah, slightly different code. We're not going to like do a deep dive into how they differ, but it's different. So we don't have as strong evidence that they're the exact same runtime performance. So yeah, this is an example of one way. So like as a general rule of thumb is that like if it's the same, if the code is the same at a certain stage of the compiler pass, like at core or STG or C++, then you don't need to dig any deeper because you know if they're same at this level, then they're definitely going to be same at the next level. So very often, like there's actually a tool I believe that I forgot who wrote it, but it basically like will actually do performance regression testing on the core. So like it will actually allow you to verify that the core doesn't change as you're like making changes, or that your core, the core of one implementation of a function matches another implementation of the function. So it's a way to verify that certain optimizations are taking place. So it's a very good way to verify a library's performance doesn't regress as you like refactor or make changes for it. If I have
That's
time,
interesting. So let's say you're writing something using vectors or something like that, or you're writing like a vector library, and you're relying on some fusion in the compiler. Yeah. And you want to make sure that this optimization you've made still causes that to occur.
Yes. If somebody knows what package I'm talking about, please link it. I'm trying to remember the name of the author of the package. It's like on the tip of my tongue, but we'll look at it at the end of this talk if time permits. But yeah, it's a very cool concept. I know for a fact that the text package does this, and they actually caught several performance regressions in text, and I think they also caught some like the documentation makes some performance claims that like this fusion rule will fire or something like that, and they actually found some cases where the documentation was wrong and fixed it. So like it's a very powerful tool.
Yeah, that's cool. Yeah. I can't even imagine finding that otherwise.
Yeah, it's called something like sorry. It'll come to me later at some point. Anyway, so going back to that. Okay, so another common task that we might have as library authors is we want to profile code. So let's say like in this case, the profile is not going to be like that rich because these functions are very simple, but I'll still dig into it just so you can see what it would look like.
And would you mind just describing like how you might like compare profiling versus benchmarking?
Oh yeah, so I say benchmarking is usually a starting point. So usually I'll benchmark if I want to answer one of two questions. Either like A, like can I write in my blog post I have a blazing fast library? So that's just like a simple sanity check I'll write before I put the word blazing in my blog post. It's just like do a benchmark and see like does this seem fast to me? And like you tend to have like it takes a while to have like an intuition of like what are good performances for like things like deserialization. Like what's a good throughput in like bytes per second for a deserialization library, for example. Like I would expect it, like depending on the domain, it might be like 100 megabytes per second or higher. Like some things can even do like a gigabyte per second of decoding performance, depending on like in some cases. So you like there's a great I think if you search for like, well, no, I was gonna say like latency numbers every programmer should know. That's also useful too. But yeah, so like that gives you like a good idea of like if you is your library in the rough ballpark. Second thing I commonly use benchmarking for is to see if there are any regressions in performance if I make a change. A good software engineering practice is to like do benchmarking on like every commit to master and then record those results so that you can just see over time if there are any commits that accidentally introduce regressions. That's another thing that it's good for.
And since criterion allows you to write things to a file, I'm assuming that allows you to have something to compare from.
Yeah, so if you go back to like the help output, in addition to, that was without, but basically, yeah, it lets you output to like CSV or JSON or JUnit output, whatever that is, and then that would, then you can then mechanically consume that. Okay, so yeah, profiling is answering a different question. So profiling is like, I have identified a problem, like either something's too slow or some user filed a performance, bug report against my package, and I want to figure out like where do I even start looking. There are some kinds of performance problems that profiling is not quite that good at identifying. An example would be like you're using the wrong algorithm, because then you just will sort of have like a flat profile where like everything is slow just because the algorithm is just running everything too many times repeatedly. The kind of problem it is good at solving is like I just wrote one particular hotspot of my program really inefficiently, and I just want to know what that hotspot is. So the main thing you do, the way
Actually,
you enable
just as a really quick example, from some work that we're considering doing on the PureScript compiler is today Colin, who works at Awake Security, discovered with some profiling that like parsing imports and checking module imports in the PureScript compiler actually takes like a third of the time to run compilation in total, and it's just an enormous like chance for performance improvement that no one has just noticed yet because we hadn't been profiling very often.
Yeah.
And so that's something that profiling just immediately showed.
Yeah. Another common example is like for a compiler, right? Like you might wonder like, okay, what's the slow part? Is it parsing, or is it type checking, or is it evaluation, or is it pretty printing? And the compiler can and then the profiler can very easily tell you which phase like that, like you just mentioned, is the bottleneck. So the way you enable profiling, so actually it's different between when you're compiling like using GHC at the command line and using Cabal. So if I believe we're not going to take this example and turn it into a Cabal project yet, but if we would, in a Cabal project, I believe the way you would do it is you'd say Cabal configure, and I think it's either -- profiling or -- enable profiling, and that will set all the right GHC flags for you. But if you're doing GHC manually from the command line, usually the relevant flags are -prof, so that just turns on profiling. But by default, turning on profiling won't actually produce a useful profile because you need to also add cost centers to your program, basically telling GHC what parts of my program do I want to measure. And by measure, I mean like, measure how much time we spend in this part of the program, or how many times I call this function, or how many allocations there were for this. So there are two ways you can actually add. You can either do it manually, so like you can actually add what's called a structured, I think it's called a structured cost center, or SCC for short, right? If I want to measure like how many times we call this go function, I would say like SCC go here, and then there'll be like in the profiling output there will be a cost center for this go function, right? But sometimes if you have a large package and you don't even know where to begin, you can just say, okay, annotate basically everything with a cost center, and then we'll go from there. And so with that, and the flag for that is called fprof auto. So that just says like annotate everything with cost center, so basically everything. And then one last thing we want to do is enable command line RTS command line options, and we use those just so we can run the program with profiling. Because even when we compile the program with profiling, it will not profile the program by default. We have to actually specifically turn on a flag at runtime to do that. Sorry, I need to actually give it the program to compile. And then the way you actually, so if I were to run the program right now with no command line arguments, it would basically be the same program as before, no profiling, but it would be a little bit slower. And for a couple of reasons. One is that when you run with profiling, GHC is like now keeping track of some metrics as it goes, so that will slow it down a little bit. The second reason why, though, is that these structured cost centers actually interfere with optimization. The reason why is that, like, let's say, like a simple question you ask GHC when profiling is like, how many times do I call this function, right? And if GHC were to really aggressively optimize the program, such as by inlining that function, that would distort how many times the function is called. Like it might either duplicate or deduplicate the function because it detects that's more efficient. But in order to preserve the user desire to count how many times you call the function, GHC will then actually, I might be wrong, but I'm pretty sure this is correct. GHC will try to avoid like changing the number of occurrences of that function. So that will interfere with GHC's optimizations. So fewer optimizations will take effect. So even right now, like we were just run example. Actually, did I turn on the benchmarking? No. Let me actually turn on the benchmarking. We will see that even with profiling off, you
still have the second main function.
Yeah. So even with profiling like not toggled on, I think I expect the benchmark to be slower than before. So instead of like 6 microseconds, some higher number. So let's actually verify that really quickly.
Is there any interference? I mean, here you're using GHC without the O2-02 optimization flag.
Yeah.
So I'd expect it to be without optimizations already. Do you know if there's
any? Oh, sorry. Yeah.
That's way slower.
Yeah. Sorry. You're right. I forgot the -02. That might be just due to not having the -02. Let's see now if it's still.
Yeah, that's a significant difference, though.
Yeah. I think part of that was just not being -02.
I just mean the optimizations alone. That's pretty impressive.
Yeah, GHC is a pretty good. Okay, actually, profiling still actually takes quite a bit down. Again, because it's really interfering with optimizations in general.
Yeah.
Actually, this one's okay.
That you hope that the changes to the optimizations are not so significant as to change the meaning of the profiling.
Yeah.
That you're getting good information essentially.
Yeah. If you can see that actually, like the two latter ones where we explicitly use accumulator passing style, their performance didn't degrade as much because we were sort of like, as the user, we were kind of optimizing the function on the behalf of the compiler. Whereas we can see that the former function that didn't have that hand optimization was depending more on optimizations that profiling is now interfering with. So now we're getting much bigger difference in performance than we got before.
Yeah, I wonder if there is a way to have GHC do as many optimizations as possible, just because maybe this turns into a hotspot where it's maybe not really a hotspot in the
so like
optimized.
Usually, I don't know if a good way to do that in general. Usually I'll use profiling to get like a rough idea of where to look.
Yeah.
And then once I do that, I'll turn off fprof auto and I'll start manually adding structured cost centers to the places I'm interested in and use that to narrow things down. So that way I kind of get the best of both worlds where I'm still getting profiling, but these cost centers are not interfering as much with optimization. So yeah, the way you toggle profiling on is then you just add this plus RTS flag, which is just -P for profiling. So yeah, here it's still slow. Again, that's probably just the difference is probably just noise. It actually looks like toggling the flag doesn't even seem to make much of a difference with profiling. Yeah, there we go. And the main thing that differs when you enable a flag is now it will produce this example.prof output right here. And I'm going to make the window a little bit bigger just to show that file because it's a bit noisy. So usually most people start by looking at this list, which just sorts functions by the amount of time that they spend in the program. Like this says that like the big cost center here was the list linked to function specifically. Well, it was the inner go function inside the list linked to function. So that's what that dot notation is there. And you can keep nesting things as well too. So if you see like something dot something, that's something that means that you have like several nestings of functions. And then it also tells you like where it was in the program. But actually, usually I don't use this output right here. Sorry, one more other thing. So this stuff at the bottom is sort of like a tree-like view of how the cost is spread out, and it's very verbose and it's pretty useless, honestly, to parse this output. So I find that often that in larger non-trivial programs, even this output up here, the summary output, can be highly misleading. And the reason why is that sometimes you can have the same function being called from multiple different contexts, and those different contexts will be sort of like aggregated together into just a single line of a performance bottleneck. But sometimes actually you're really interested in one specific context. The best way I can describe it is sometimes in profiling what you want is like a stack trace for your hotspot. You want to know the context for how you got there. And this summary at the top doesn't really give you that. And in theory, that kind of information is buried in this more detailed output below, but that's very hard to parse. So very often I will use a helper tool that I like called Profiteer, which is really, sorry, it would be, for Nix, it would be Haskell packages.profiteer.
And by context here, are you referring to, you've got a function that may be expensive, and it's called within function A over here, and then elsewhere it's called within function B over here. And you want to see the difference between those two rather than those two lumped together?
Yeah, it's a combination of, yes, I would like to split out those two separate functions. So that in itself is valuable, so I'm not conflating one hotspot with another unrelated hotspot. The second reason why is even for debugging, even if it were just one single occurrence of the function, I want to know what chain of function calls got me to that function, because that can help me better understand. Like that actually helps a lot with the algorithmic part. So like very often, sometimes I can see in that chain of functions that there's some problem in my algorithm that could be improved, for example. So the way you would use this Profiteer tool is you would say Profiteer, and then you give it the dot profile that was generated. And then it'll generate another file, which is basically the same name, but .html. So if I open that file, okay, so let me just switch to the browser over here. Okay. So what it does is give you sort of like a tree view way of browsing your program's performance. You can actually view by time or by allocations. And for this, we'll just do time. And you can either use this tree view on the left, or you can use the viewer here on the right. So in this case, is like the top level is just the main function. So we can double click on just this big purple blob to dig in. And actually, we have to go several levels down before it's like starts to split up. So it says like, okay, so main calls default main, which calls default main with, which calls run mode, which calls with config, and we just keep going down until we start seeing something interesting. Oh, here we go.
So this all looks like a criterion related functions?
Yes, this is basically like all criterion related functions. So here is where it starts to split up. So he says there's a run and analyze function which calls three separate functions: run and analyze one, encode, and read JSON reports. It's really hard to see, but I mean there are two like thin purple and indigo stripes here on the right, and most of the time it's dominated by run and analyze one. So I'll just keep digging into run and analyze one until we get like a more meaningful split up of the performance. So here now we can see that, okay, most of the time is spent in run one, and then like maybe, I don't know, 10% is spent in this analyze sample function. So I want to keep digging into run one, keep digging. Okay, yeah, here we go. So then so here's the weekend. It says the weekend normal function is called on either list length 2 or list length 3 and list length, and the program spends a various amount of time in each one. One thing that's important to note is that at least when profiling a criterion program, the amount of time it spends in each of these functions is not really informative, because again, criterion is just going to always use up its time budget, right? Or like if it decides I have 5 seconds to run that function, I'm going to spend 5 seconds on it, right? Regardless of how fast that function actually is. So it's actually more informative to use profiling in this tool on like a real world program. But this at least shows you what the tool's user experience is like. I can like then dig into, let's say this one right here, list length 2. And then that says, okay, list length 2, some of that cost is the go function inside of it, and some of that cost is, if you see in div, that means it's its own cost without like calling out to some other function. And we can just, I think right here it just stops because there's nothing underneath list length there's no function that list length 2.go calls, so that is the entirety of the cost. So I find this is a very rich way to understand your programs. It provides that stack trace that is like sorely missing from the default .prof output.
And Vladimir had a question that you might want to check in chat.
Yeah, let's see.
Saying it could be useful to dig inside the function and see proportionally how the time is spent there. Though in this case, the functions are trivial. Actually, not a question. I suppose more of a comment. Okay. But just to make sure you see it.
Yeah. So yeah, I think in this case we couldn't keep digging further because like once we got to that go helper method, then there was no function that was transitively calling, so then there was no deeper performance breakdown. Let me see where we're. Okay, so yeah, another thing I wanted to cover really quickly is a little trick I use often for optimizing some libraries. So let's go back to the example program that we had before. So I'm going to now introduce another list type, which I'm going to call iterator. And the difference between list and iterator is that iterator is going to be defined in a non-recursive way, meaning that like an iterator will basically be some starting state and then a step function. So given a state, maybe generate an element and then a new state. So the idea is that like if it's a just, that's a new element of the list, and if it's a nothing, then that's like a nil or an empty or the end of the list.
And the state here is kind of like an index or like a count for the most part.
A state in this case, it could be literally any type, right? It could be a number, it could be the unit type, it could be a record, or some permutation of all of them. Also, we're actually going to use a language feature here called existential quantification, which basically allows us to add type variables to the right-hand side of this data type definition, but that don't show up in the left-hand side of this definition. So in other words, we can have a state inside this iterator type, but the user who uses our iterator doesn't have to know what the state is. So the only thing the compiler will check is that S is consistent, meaning that if this first field here it happens to be an int, then the step function needs to be a function from an int to maybe an a and an int. So as long as these s's match, then the compiler is happy. But other than that, it doesn't care which type we put in there.
Got it.
Yeah.
And you're responsible for providing that when you fill in the constructor for iterator.
Yeah. And so the reason, another common question people have is like, why is it called for all here, even though this is called like as existential quantification? Like, shouldn't this be exists instead of for all? I think the best way to explain it is that it makes more sense if you write out the type of the iterator constructor. So if you were to write out the iterator constructor type, it would be for all s, given an s, and then a function from s to maybe as. Give me an iterator of a. So for the iterator type, the iterator constructor type, the s is universally quantified. So I think at least that's the closest justification I can think of for why they use the for all keyword right there. Okay, so now what we're going to do is implement a list length method, or sorry, an iterator length method. So iterator length iterator a int. It'll be very similar to our ladder to list length method. So first off, we get the starting state, and we pattern match on it to get the starting state and the step function. And then we'll call a helper function starting with that and say, okay, so go with our state, equals, so we call the step function on our state, and then we say, okay, well, if it returns nothing, then we can actually kind of write it similar to the other function, so like similar to this function right here, just for starters, and say, okay, if it's nothing, return 0. If it's just some element, which we'll ignore, and then x is, then it'll be 1 plus go x's. Yeah, wait. Yes, that's correct. And it's not. I shouldn't use x's. I should just call it state prime. It's not a list. It's the state. Okay, that type checks good. Okay, and so now let's actually just run another. We also need an example iterator of numbers, which will be again very similar. Sorry, iterator. Sorry, it'll be iterator start step where. So again, we can pick any accumulator type we want. In this case, we're going to use an int as the accumulator, so start is going to be 0. That means our step function, if you were to give it a type, would be int to maybe. In this case, it's like a little bit confusing because both the state and the element type are both int. But this would be the element type int, and this would be the state type int. And we say, okay, so step with the starting state of n. We'll first check to see, is n less than or equal to 1,000? If so, then return just the element n, and then an updated state of n plus 1. Otherwise equals nothing. I think that's right. Okay, yeah. And then lastly, we'll benchmark this. In fact, let's just make this the first one, so we can just cut to the chase. We'll call it capital I for iterator. So this will be iterator length, iterator numbers, sorry, and then GHC.
So just iterator number, no S.
Oh, right. Oh yeah, let me fix that then.
I just saw that this channel has been categorized as an educational game.
Oh, nice. Well, I mean, Haskell kind of is like it's that fun.
Yeah.
Not even joking. So okay, benchmarking the iterator. Let's see how it does. So 70 microseconds. That's slower. And then 24 microseconds for the list. So you might wonder, like, why would you even do it this way, right? So actually, it turns out there is a good reason to split it out into this implementation. And that's because there's one thing that GHC does very well, is that it's really good at optimizing non-recursive code. So what I'm going to do here is I'm going to implement a functor instance for iterator. And we'll see why in just a second. So fmap given an iterator with a certain starting state and a step function. It'll be a new iterator with the same starting state. Thank you. So a new iterator with a same starting state but with a new step function. So step function given a state will call the old step function with the same state to return, a and a new state. And then we'll just transform the element and keep the state the same. So that type checks, good. All right, so now what I'm going to do is say, okay, so iterator numbers 2 equals iterator int. It has type iterator int. It's going to be fmap id iterator numbers 2. And also for comparison, actually let's call this mapped iterator numbers. Now let's also do a side-by-side comparison. So mapped list numbers, so that's going to be a list of int. Mapped list numbers equals map id list numbers, and this should be just iterator numbers. And so I'm not going to we're going to dump some core here in just a second. So I'm going to just make main equal this. Okay. Oh, sorry. There's a type. Oh, sorry. Fmap. Oh, actually, I didn't implement functor for list. So let's do that quickly.
And just as a quick summary,
yeah.
You're implementing fmap here in order to demonstrate some differences between the two of these in terms of what GHC
optimizes,
compiles them to?
Yeah, that's correct.
What sorts of optimizations? Okay.
Yeah. So let's get back the this. So like people familiar with functor know that one of the functor laws is that fmap id equals id, or if we were to expand that, fmap id x's equals x's, right? Meaning that they should produce the same result. And so they are equationally the same, meaning that semantically they give the same result, but like in general they're not guaranteed to actually like generate the same machine code. So like if you were to fmap id over a list, it might actually, even though it's still the same result, it still might like waste its time looping over the list, at least for an unoptimized list. So that's one of the reasons why I didn't use the list type from base, because base actually has some rewrite rules to make this more efficient. But without those rewrite rules, the GHC will just sort of do the dumb thing and like go over the list again and call the identity function on every element of the list. But when you write things in a non-recursive way, like the iterator type, a GHC is much smarter. It will actually generate code that is exactly the same. So let's see. Yeah, here we go. So it says GHC was smart enough to optimize mapped iterator numbers. It says, okay, this is exactly the same as iterator numbers. And the reason why is because when a type and all its utility functions are implemented in a non-recursive way, GHC can be much more aggressive about inlining things than if it were operating on a recursive type, like the naive implementation of a list. So because the iterator type definition is not recursive, we can just verify that really quickly. So yeah, the iterator type is not defined in terms of itself. It's not a recursive data type. The iterator length function is not. There always will be one source of recursion in the system. So specifically, the only thing that's recursive here is the iterator length function, right? But everything else, like the definition of fmap for an iterator down here, that's not recursive, right? It just like modifies the iterator and then it's done, right? And so what we've done essentially is by designing things in this way, we've pushed recursion to the edge of the system, where the edge in this case is the iterator length function. And so because we have a larger non-recursive core, that gives GHC more room to inline things aggressively and optimize. So that's why GHC was able to figure out that this mapped iterator numbers generates the exact same code as the original list. So fmap id on the iterator, so fmap identity over the iterator is the exact same as the original iterator. They'll both generate the exact same assembly code. Contrast that with list, where it doesn't have that same optimization, right? It just says, okay, yeah, I'm going to be calling fmap for lists using identity function. I'm just going to be for the list, and it's going to be a little bit slower. We can even verify that, so we can now we can look at the benchmark for. Oh, sorry, let's benchmark the mapped versions right here.
And as you're typing that out, just like kind of a real world question. One place that you'd mentioned that you'd seen some of this, or that you'd written yourself, some of this more iterator style, was in like streaming libraries in the Haskell ecosystem.
Yeah, So go ahead. Sorry.
Sorry. There's a bit of a delay, so some of the conversation is tough. I was just going to say, as far as making that decision between using the iterator style or the more usual GHC like list style, using like the profiling and benchmarking tools that we've been talking about in this session, do you have ideas on how to use basically benchmarking and profiling to decide which one of those would be the right choice for my library I'm writing?
Benchmarking and profiling would both help, I think, a lot, but there's something else you would need. You also kind of just need an intuition for how people are going to use your library. So like we saw, for example, that like iterators have a slower constant factor than the naive implementation of a list, right? But we do know that like when you apply transformations to them, like map or maybe concat map, that GHC can be much better at optimizing those successive transformations sometimes. So at that point, you have to like answer the question, like, how do I expect people to use my library? Will they mostly be doing a simple thing, like just produce a list, consume it? Or will they be like taking a list and transforming it a whole bunch before they finally consume it? So it just requires some intuition for how your users are going to use the library. Or, I mean, because Haskell is really good at providing overloadable interfaces, type classes, like we got functor, we got foldable, we got monoid. You could just provide both, right? And then just like provide interfaces that work for both implementations and let your users select which implementation they want to use. So that's another way you can sort of navigate that trade-off if it came down to it. So let's now check to see. So what I would expect to see is that now iterator might still be slower than a list, but the performance difference should be a little. Oh, actually, yes. Let's see, 95 microseconds for that. Yeah. So now the performance difference is narrowed because iterator is basically the same code as before. We verified that using the core, but now a list is slower as a result of applying the map. And you can imagine as we apply successive transformations, the list will just keep getting slower and slower, but the iterator will stay roughly the same. It's much more stable and predictable performance, even if it has worse initial or constant factors. So yeah, I find like a lot of people are not aware of this little trick that GHC can do a really good job of optimizing non-recursive code, and sometimes that can be an easy way to get performance wins for code that's streaming or recursive in general. Yeah. So I think we're at the hour mark. So before we conclude, I just want to ask the audience if anybody had any questions that they want me to answer before we wrap things up. In fact, while you do that, I will just look for that thing I was talking about before, the introspection testing. I think that's what it's called.
Yeah, right. Or else as soon as you close out the stream,
yeah,
you're going to think of it immediately.
Yes. I think that's what it's called. Inspection. I think it's inspection testing. Yes, this is it. This is exactly the package I was looking for. So it's a GHC plugin that you can use to verify at least and minimally that two functions have the same core. Yeah, here's an example. So like there are two implementations of the left-hand side, two functions called left-hand side, right-hand side. They have slightly different implementations. And you just want to check, do these two functions generate the exact same core? And it can tell you that, for example. I think there was one other thing you can do with this, which is also like you can see like there's a function like remove all type, like does it specialize correctly? Because sometimes it can be hard to guarantee that a specialization occurs, or does not use core of. Yeah. So anyway, there's a and the name the name of the person, I don't know how to pronounce it, but it's Joaquin. Right. Yeah, that's his name, and inspection testing. He's given a few talks on this, and there's a blog post as well. So if you just search for that, you'll find his talks and/or blog posts on this subject, which are very good. I highly recommend them. So they're a great way to keep performance stable if you're a library maintainer.
That's cool, especially that it's able to check a number of other, not just that two representations are the same, but it doesn't have type classes. Yeah. It doesn't have these other results. That's very cool. There's also a question in chat.
So does the base list type have special rewrite rules to make things like fmap id as fast as iterator version? The answer is yes. In fact, we actually could just test that really quickly. Like, let's actually now use the Haskell list type. So example 0 is a list of int. Now let's just example 0 equals. I'm pretty sure it will work for this, although I haven't tested it. It's been a while since I've looked at this for Haskell lists. So let's use map. Let's do, map id example 0, and let's just check to see if the core there is basically oopsies. Not lit. Oh, sorry. Yeah, it's that. Yeah, I'll get to your question about the intermediate forms. That's a very good question. Yes, well, a lot to optimize for some reason, or maybe a lot of core to dump. Oh, sorry, yeah, there we go. Yeah, so here's an example of GHC optimize. So this was the original list, and we did map id and GHC optimize that. And the only reason that worked was because of rewrite rules in base, which are designed to give you efficient list transformations. So that's another way you can get. That's another way you can give good performance with a library. Is that like you do the obvious naive data type, which already has good constant factors, and then you add rewrite rules so that you can still get reasonably predictable performance as you transform it. And that's essentially what base does for the list type. So I'll go to the next question, which is, were all of these intermediate forms developed for Haskell specifically? So core, the answer is like mostly not. So core is sort of like a, well, I mean, as a computer file format, you know, core is, I mean, I don't even know if it doesn't actually go through a file format, but like as a data structure in some library, it's Haskell specific. But like a system FC is something is a variation on system F, which is a very well-trodden programming language baseline. It's like a very common language used in type theory for describing a lot of things, and it's sort of like a foundation for a lot of type theory. And Haskell takes that foundation.
To Microsoft Research, FC was produced for Haskell, or produced by Microsoft Research and then used in Haskell in 2011. Yeah. So actually quite new, and before it was System F.
Oh, really? I didn't realize that.
It was System F and then a symbol, and I'll have to leave it there.
Okay.
But
is it omega? Is the symbol omega? Like the W, Greek W?
Yes. Okay, it was System F Omega, and then in 2011 it's replaced by the newly created System FC.
Yeah, so what I said before was slightly wrong, actually. So it's Haskell's closer to System F Omega rather than System F for all the pedantic type theorists in the audience. And then they added system FC, which I believe is like system F plus constraints, I think.
To quote, we introduced system FC, which extends system F with support for non-syntactic type equality.
Okay. Then I still think the C is probably for constraints. But yeah, so basically a way to say like to encode equality assertions in the language. Okay, so so system F, at least as a concept exists outside Haskell, but like as tooling is very Haskell specific. STG is definitely Haskell specific. Like in theory, you could actually reuse Haskell's STG logic. Like maybe you write your own front end to STG and then use the Haskell pipeline for us to optimize that. That might be a thing. But yeah, no other compiler toolchain uses STG as far as I know. I think the same is true for C++. I think it's unique to the Haskell toolchain. So I think having those intermediate stages, I think it's just because like they are useful. Like if we were to compare to like say the LLVM toolchain, right? Where you just like I think LLVM toolchain mainly has like just one intermediate representation or IR, where Haskell has multiple ones. I think it's just because like Haskell, because it's a functional language, there are like lots of different places in the compiler pipeline where a certain optimization is more appropriate, right? So like for example, like rewrite rules make a lot of sense to apply at the core representation of the pipeline, right? They don't make any sense to apply at like the C++ or the STG stage of the pipeline. Whereas like, low level like register allocations and stuff like that, they make more sense to apply that optimization at I think the C++ stage of the pipeline. I don't know. I'm probably just like spitballing here. So I think it's just because Haskell's a language that has like I think out of all the functional languages, Haskell does like the most non-trivial optimizations. So like because of that, I think that's the constraint that causes it to have like lots of different compiler stages compared to say LLVM. Okay, so the next question is, are you able to provide rules of thumb around performance in general? In other words, what cases should we intuitively reach for Bing patterns? I would say like in general, do the obvious and dumb thing. Like the Haskell compiler has gotten really good at taking dumb code and making it really fast. I wouldn't like do premature optimizations if it's not profile guided. I mean, there's some obvious profile hygiene that's good to do that can't hurt, and it's usually the right thing to do. An example would be like past the accumulator state version of list length we wrote before. Like, it was easy for you to do, you know how to do it, just go ahead and do it. It's like, it's one less thing to worry about. But I find that the compiler is so good at what it does that sometimes just doing the dumb thing and then plus profiling often gets you pretty far. Like Bing patterns are a great example of that. They used to be like, the Bible of profiling is like you should use strictness annotations on your records and then on strictness annotations on function arguments. And that was the conventional wisdom for a long time ago. At least back when I started Haskell programming, that was the conventional wisdom. Now I feel like it's not as true as it used to be. The compiler is really good at strictness analysis, and I find very often adding strictness annotations to records or function arguments has very little effect, either as measured by profiling or as seen by inspecting core. So I would say like don't do an optimization unless it's supported by profiling or core inspection. Because the compiler has gotten really good over the last few releases. And yeah, okay, so I think that covers most of the questions. So yeah, I think we'll wrap it up today. And also, if you have any suggestions for the next talk, feel free to either here in the Twitch chat afterwards, or you can message me on Twitter, or email me, or email me. I'm Gabriel@awakesecurity.com if you have ideas for the talks. Either way, so just give us ideas, and because currently we don't have a topic planned for next month's session. If nobody suggests one, we'll come up with one, but we'd like to take suggestions from the audience. So we invite and welcome suggestions for topics to cover for next time. Other than that, I think that we're good for today. So thank you, everybody, and we'll wrap it up. Yeah, and you're very welcome.
See ya.